Okay, there's our video. Okay, so we're going to do this one, and we're going to do this one. So let's have a peep. Memory management part 3. What's all this about? So last week we did a lot of theory, and we did all the different virtual memory stuff. Did a lot of numbers, which were horrible, and we mentioned these thing called paging algorithms. And the whole point was we had this sort of idea, right? A simple example. I've added this slide to these notes just on my deck. It's in either earlier decks, but just as a reminder what we're talking about here. So what we sort of said was this was a simple program with 24 what we call pages, right? And typically 4K in length. And this is the process as it appears in virtual memory. If you had a process, that's I'd say a very simple example. Say it's Excel, right? Really simple example that I gave you. You opened the file, you did some work on it, and you saved it, right? The order of use pages was I would load up the code here, then I would get to here, then I would get to here. Oh, then I had to jump to a function call to do some work on a formula. So that was order of use 4 and 5, and that was page 20 and 21. And then when I finished that, I wanted to write it out, and that function was here in the way the program was organized in memory, right? So that would be 6 and 7. So 7 pages of the 24 code I would need. But in reality, I said to you, the DRAM space is always less than what you have in what's called virtual memory, right? This is our physical DRAM. So what would happen is, as I ran through the code, the first chunk would come in, then the second chunk would come in, and the third chunk would come in. Then I would go down to 4 and 5, so the 20 would come in, and the 21 chunk would come in. So now my DRAM is full. But now I want to load in chunk 13 and 14 because I want to save out the work I've done in Excel. But the problem is my DRAM is full. Remember, I can't run any code unless it's in DRAM. I can't run code directly from here. Okay? This is like as viewed in hard disk or whatever. So my problem is I have to bring 13 in here. So the problem is I have to get rid of one of these. So there are algorithms to decide which one do I get rid of. And one of the algorithms is FIFO, and we're going to do that algorithm. And what FIFO would say is, well, the one that is in the longest I want you to get rid of. So in this case, number one would get hoofed out, and 13 would go there, and number 2 then would get hoofed out, and 13 would go, 14 would go there. All right. So what we're going to look at is those paging algorithms. There's a few different ones we're going to look at. So a couple of pages of theory before we get into the numbers. And when we get into the numbers, please be interactive, right? So in other words, as we're going through it, I'll be saying what do you think is the next one that's going to come in. And feel free to join in and say what you think. Don't be afraid if you get it wrong. The whole point is if you get it wrong, you learn from that. Don't use the microphone, but just use the chat, all right? And we'll have a bit of fun. I say this hopefully won't take too long, but we'll see how we go. So typically what's happening here is we're moving pages from secondary memory to primary. In other words, there's pages of the program or the process as it's viewed is coming in from hard disk or SSD, not SSD, into DRAM. So we're swapping in. Similarly, there are some times where we might need to swap out, right? You may actually remember when we did suspension and resumption in the schedulers. Remember that? And processes. And we said sometimes a process can be hoofed out of DRAM into secondary memory, it can be suspended. Well, that's actually a prime example of you're taking stuff and you're throwing information that had in DRAM, like it's process control blocks, it's PCBs, and you throw it out to secondary memory. So that's an example of paging out. Right? But here's the message, right? The problem is that when you do this, there's overhead, right? And it takes time because remember, a hard disk is a much slower device than DRAM. So we would like to minimize the amount of times we have to hoof pages out of DRAM because it costs us time, and therefore it means our overall way our computer runs looks slower, right? And you've all seen this, you know, if you don't have enough DRAM, you run Excel, Word, Chrome, whatever, all at the same time, and the thing crawls, right? If you don't have enough DRAM. That's why it's swapping stuff in and out all the time. So the amount of DRAM we have makes a big difference. So here's a question for you. Here's the first question of the day. Is the number of page faults? Do you remember what a page fault was? Do you remember what a page fault was? We did minor, major, and whatever, error 1 or whatever it was. But what's a major page fault? Can you remember what a major page fault is, anybody? From last week? There was about 50 here. So hopefully someone will remember. Any ideas? frantically typing there. Silence, a bit early on a Wednesday morning. It's just a term given to when you swap out or bring in. So in other words, the process of bringing that page into DRAM, that's a page fault, okay? Or the fact that, you know, I brought them in the first place is a page fault. So do you remember the question I asked you last week? For this process to run in total, how many page faults were there in total for that program to run? Can you remember the answer to that? I'm getting beeps, but I'm not seeing anything on my chat. Are you guys putting, someone go on mic and tell me, are you guys putting something into the chat and I'm not seeing it? Ah, question mark. 7. Yes, Andre is correct. There were 7 page faults, right? So every time we have to bring something in from virtual memory into DRAM, it's a page fault. So it's not that there was 2 page faults, right? There was actually 7 because there was nothing in there at the when we started in those 5 slots. So there was 1, 2, 3. Then we brought in 20, 21. That's 5. Then we brought in 13 and 14. That's 7. And we threw out 20 and 21. Okay, so there was 7 page faults there. So let's go back to the question. Is the number of page faults proportional or inversely proportional to the number of pages we can fit in DRAM? So what that means is, if we have more DRAM, do we get more page faults? Or if we have more DRAM, do we get less page faults? Which is it? Anybody want to hazard a guess? If you think about it, right? If we have more DRAM, do we get more page faults or less page faults? That's essentially what that question's asking. All of the above. Very funny. Which is it? Less. Okay, you get less page faults, right? Because when you start running a program, you'll have loads of DRAM and you'll have to throw out less. You'll have to throw out less pages, so you get less page faults. So that's a good idea, right? So when more DRAM, you get less of these, so your program runs quicker, and you'll see that when we do the examples. Okay, that's all that says. So let's have a talk about these algorithms, right? We're going to do 3. We're going to do FIFO, we're going to do LRU, and we're going to do a thing called optimal, which isn't actually a scheme, right? It's the ideal case, the absolute ideal case. So what we do is, if we do these 2, FIFO and LRU, and we compare them to optimal, we'll see how good they get to the ideal case, which is optimal, right? What is the optimal scheme is the question we ask here. You know, is it one of these? Remember, is it random pages getting just picked? Any page in there, we throw it out, right? So in other words, would it be better off just pick random, any one of those and throw it out? Or FIFO, we talked about. LRU is very close to FIFO, and less frequently used is another one, right? So the optimal scheme is remove the page that we do not need for the longest time in the future. That's a very strange sentence. What it means is, if you were to look in the future, if you were to have a crystal ball and you have a certain amount of pages in DRAM, and in the future you could say, I don't need this page anymore, you'd get rid of it, wouldn't you? Whereas you wouldn't get rid of the one, say, you're just about to jump to or use. So that's the ideal case. Don't worry, we will see it in operation in a few minutes if you don't get it yet. You would need to be clairvoyant, right? You'd need to have a crystal ball. So it's idealistic. It's not in reality. You can't get an optimal scheme, but we can get as close to it as we possibly can. Okay, so let's compare optimal versus FIFO. Right? Don't worry, we'll step through this. So here's a really, really simple example. Right? So what does this diagram mean? So get used to these diagrams, because this is what you're going to be doing in the lab next week, and some of these are going to definitely crop up on your CA2. And I'm going to tell you now, and I'm going to stress it a few times before your CA2. Your CA2 is harder than your CA1 because of those semaphore and those scripts questions, right? These questions, I think, are the easiest questions. So you really, really should make sure you can do these page management questions, because they are the easiest marks you will get on CA2. Okay, can't say it more straightforward than that. So make sure you know how to do these. So what is this? So what this is this is a process. It's got 4 pages, right? It's got 4 chunks. And these are the order which those chunks are used, right? So in other words, say I had a program, chunk 1, 2, 3, and it read all of it. It was running code in chunk 1, then it needed code in chunk 2, then it needed code in chunk 3, then it needed code in chunk 4. Oh, and then it had to jump back to chunk 1, then it went through chunk 2 again. So it's a big loop, right? And eventually it finishes and decides to exit after going back to chunk 2 there. So that's 10 chunks, and that's the order in which the code revisits the chunks, right? These little grid here, I'm going to compare FIFO with OPT. So I have room for 3 chunks in my DRAM. This is my DRAM here, right? And this is my DRAM here for OPT. So I'm going to compare FIFO with OPT. So you mightn't get it until we go through the example, but hopefully then you'll get it in a second, all right? So the first one, I need chunk 1. Well, obviously we have to bring it into the DRAM, right? Just like we did back here, right? So this is very similar to me writing this as 1, 2, 3, 20, 21, 13, 14 across the top, and then I had 5 instead of 3. Okay, that's all this diagram means. So chunk 1, grand. Chunk 2, what am I going to do here? So I bring in chunk 2. That's easy. We'll do the first 3. Okay, that's what it would look like after 3 chunks. And how many page faults have I had? In each of them, how many page faults have occurred there? How many FIFO page faults were there? Anybody? 3. Well done, Paul, right? So in other words, I had to bring in 1, then I had to bring in 2, then I had to bring in 3. Same for OPT. Now, let's have a look. What am I going to do here? I need to bring in chunk 4. I don't have any space left, so I have to get rid of something. So we'll do FIFO first. FIFO says get rid of the one that's been in there the longest. Which one will I get rid of for FIFO? Yeah, exactly, right. Really simple stuff. Piece of cake, right? So I'm going to bring 4 in there, so I'm going to have 4, 2, 3. But before I write that down, let's have a look at this one. Don't look at the slides ahead, by the way. Do yourself a favor and do these as we go along. Now, optimal is totally different, right? This is what I have in at the moment. I'm going to bring in 4. What optimal says is have a look in the future and get rid of the one that's furthest in the future, right? So in other words, I'm bringing in 4 here. So I look along the top line to the future and I find the one there that's of the ones I have that's furthest away. Which one would it be? Would it be 1, 2, or 3? It would be 3, wouldn't it? I wouldn't get rid of 1 because I'm just about to use it. I'm then just about to use 2, and 3 is definitely the furthest away. So you can see immediately I've started to diverge here, right? Now I have different stuff in my DRAM. So now we'll do it again. FIFO. Which one of these will I get? Which one of these has been in the longest? Which one will I get rid of? Yeah, easy, yeah? Get rid of 2. Now, which one of these will I get rid of? 1, 2, and 4. Look closely again. There's a step you need to do before you blindly look along the top. Oh, look closely again. Think about it sensibly. You're not thinking about it sensibly. What's the whole point here? The whole point is to minimize the page faults. The whole point is to minimize the amount of times I have to throw something out and bring something in. So I'll ask you one more time, which one do I get rid of? Anybody? Exactly. Well done, Reese. Why would I get rid of something that's already there? So in other words, I don't have to get rid of anything. And so now we immediately see the advantage of optimal, right? I now have one less page fault. I didn't have to bring in anything. 1, 2, 4. 1 is there. So we'll go back and do the next one. FIFO. Bring in 2. Which one will I get rid of? Well done, Luke. And optimal. Which one will I get rid of? Yeah, well done. It's already there. Okay. Now, 3. FIFO. Which one? Anybody? 4. Yeah, looks good to me. Now, here's 1. I'm bringing in 3, and I've got 1, 2, and 4. So I'm going to have to get rid of something here. So which one will I get rid of 1, 2, 4? Remember, I'm actually here. Sometimes people write these and they put in the 1, 2, 4 here again, which is fine. You can do that as well. So which one will I get rid of? Okay, now we see people. So Andre says 2. Anybody else? Is Andre right? Yeah, I think he's right. It's 2 because I'm at this point here. I'm bringing in 3. I've got 1, 2, and 4. Well, I'm not getting rid of 4. I'm not getting rid of 1. So 2 looks a good one to me. Okay. Next one. FIFO. Which one? 1. Yeah, pretty simple. FIFO, right? Now, 1, 3, and 4. Which one? For OPT. 1, 3, and 4. Which one? None. Well done. Looks good to me. FIFO number 1. Which one? We get rid of, I'd say, which one? 2. Exactly. FIFO's a dollar, right? Pretty straightforward. And this one I have 1, 3, and 4. And I need to bring in 1. I don't have to do anything, do I? It's already there. Right? And then the last one, and you can immediately see there might be an issue here because I don't have a future. We'll talk about that in a second. So which one will I get rid of? I'm bringing in 2. Which one? FIFO. 3. Yeah. Now, OPT. I need to bring in 2. I don't have it in there, so I'm going to get a page fault. But which one do I get rid of? I don't have a future. What do you reckon it does? What do you reckon it defaults to? What does it fall back on when it has a choice like this? So what it does is it falls back to FIFO. All right. So when it has a choice, yeah, well done, Andre. When it has a choice, it falls back to FIFO. So I don't have a future, so I can't figure out anything here. So which one will I get rid of if I fall back to FIFO here? Yeah, exactly. Right. So there we go. That's what we end up with, right? So here's the question: why is optimal better? Who's been awake? Why can I say this proves that optimal is better? Exactly. Right? I have 6 versus 10 page faults. Okay? So therefore, my program will run much quicker. But sadly, optimal doesn't exist. It's idealistic. But it's a great one to compare against, right? So let's keep going. So what we saw was that was when we had 3 pages of DRAM. So what we also thought in theory was that if we had more DRAM, would we get a better result? Okay? And there's a very, very simple example whereby if I had the exact same, right? I upped my DRAM to 4 pages. Instead of getting 6, right? Instead of getting this, I would actually get this, right? So page faults were 4. So 4 is better than 6. So just by upping my DRAM, that sort of proves that theory as well. So another one. let's compare a different example, just to make sure everybody's getting optimal, because optimal is probably the trickiest one. All right. So let's do this one together. 3 versus 4 pages. A different, slightly different example. Now there's 6 pages in my program here, see it? And I go 1, 2, I go all the way through, and then I hop back to 2, then to 1, then to 6, then to 5. So I'll hop around a bit there. So let's see what happens with optimal 3 pages versus 4 pages. So we'll do the first 3 quickly. Fair enough. Optimal, if I bring in 4, what do I get rid of? In this example here. Somebody says 1. This is optimal. 1. So 1, 2, and 3. There's 2. There's 1. I don't see 3. So why in the world would I get rid of 1? Yeah, I get rid of 3 because I don't have it in the future. Yeah. So I will get rid of 3 here. Hopefully everybody sees why. And this one I just bring in 4. Okay. Do it again. Optimal. Bring in 5. What do you reckon? I've got 1, 2, and 4. Which one do I get rid of? You're obsessed with 1, Luke, but Luke, I think you're thinking of FIFO. It's optimal, right? So I'm bringing in 5. So which one don't I need in the future? Well, I need 2. I need 1. I don't see 4 there at all. So I'm going to get rid of 4. So it's going to be 1, 2, 5. Now this one, I have 4 choices. I need 5 to come in. Which one will I get rid of here? Luke says 3. Okay, we have a nice difference of opinion here. Okay, so let's work through it. We have 1, 2, 3, and 4. And we're definitely not going to get rid of 2 and 1 because we need that. So we have a choice between 3 and 4. And what did I say to you? Yeah, we have a choice between 3 and 4. And so what you do is you throw out the one that's been in the longest. You revert to FIFO. So 3 has been in the longest, so I'm going to get rid of 3. Okay, so the people who said 3 are correct. Be careful with that. Every time you have a choice with optimal, you make that choice based on FIFO, but only when you have a choice. So let's do this one, 6. Up here, 6. Which one will I get rid of, 1, 2, or 5? Pretty straightforward, I think. Any ideas? 1, 2, or 5? 5, yeah, exactly. Because there's 1, 2, there's 1, there's 5, yeah, cool. And 6, which one will I get rid of here? 1, 2, 5, and 4. Again, pretty straightforward. 4, yeah, looks good to me. Okay, so 1, 2, and 5 are there. There is no 4, so we're good. You're getting it. This one, 1, 2, and 6, optimal. You need to bring in 2. Which one will I get rid of? Well done, Luke. None. It's already there. And it's already here as well, so we can keep going. Ooh, and there. Oh, so 1. It's already there. 6, it's already there. So 5. This one here, right? Bring in 5. 1, 2, and 6. Which one will I get rid of? I have no future. Yeah, so I revert to FIFO. That's 1. And this one, it's already in there. So by increasing the DRAM, even for this example, I got page faults 6 versus 7. So as expected, the one with more DRAM, less page faults. Does everybody see that? Hopefully you do. Okay, so we'll do more in the lab. So let's have a peep here at LRU. Okay. So let's get rid of that one. And what is LRU? So as I said, I told you we do LRU, OPT, and optimal, right? So what's this LRU thing? So LRU is remove the page that has been least recently used, same as FIFO. So a little bit odd, right? In that it's quite similar to FIFO, and you get very similar results, but it's not actually the same algorithm, right? And this one, I'll be honest with you, if I had to pick which was the easiest one to do, it's FIFO. Then LPT is the hardest. LRU can be tricky because people just do the method wrong. If you do the method right, LRU is simple. Okay, so let's have a look at LRU, right? So here's an example of FIFO versus LRU, a really simple example, right? I've got 6 pages I'm bringing in. I've got 3 in my DRAM, right? So this is FIFO here. So we know how FIFO works. 1, 2, 3 straight in. I want to bring in 4. So 1 is in the longest, I get rid of it. 2 is in there. And then I want to bring in 1. So I have to get rid of whichever one's in the longest. Well, obviously 2 is in the longest, right? So that's FIFO. We know that at this stage. Now look at LRU. We end up with a different result here, but the exact same example. So first 3 are the same. 4. So I want to bring in 4. So what do you do with LRU? With LRU, the method is do not look here, right? You look to the left on the top line. So if you think about it, when we do FIFO, we look at the DRAM grid to the left. When we do optimal, we look at the top line to the right of where we are. And when we do LRU, we look top line to the left. Do not look here. Look here and pick the one that's furthest in the past. So in this case, I'm bringing in 4. Of the ones that are in here, 1 is the furthest in the past. I'm going to get rid of it. So it replaces it. Now, at the moment, it's the same as FIFO. But look what happens now. 2 is in there. 2 is in there. Now I want to bring in 1. If I were to do FIFO, I get rid of number 3. Is that right? No, sorry, I get rid of number 2. But if I want to do LRU, I look to the left. 2, 4, 3. I get rid of 3. Okay, so it's a different answer. You start seeing different, as you move across the grid, you start seeing different results. Okay, so what I'm going to do now with you is I'm going to give you a sneak preview of your lab next week, right? Just let me turn this on. And we'll work through one of these. Go find it first. Okay, so what in the world is this? I hear you ask. All right, so this is what you're going to be doing in your lab next week, right? We've got 3 FIFOs, 3 LPT questions, and 3 LRU questions, right? So the questions are, and the data in each one are the same, and the whole point is you do each algorithm and then you compare them, right? So what I'm gonna do is we will do a FIFO. We'll do 1 FIFO and we'll do 1 OBT this morning, okay? And then we'll do all the rest in the lab next week. So what I'm going to do is now that you've hopefully got the idea, I'm going to give you about 8 minutes or so to have a go at this first one on your own. So this one here, right? Don't do the other 2. This one here. This is FIFO, yeah? So when we need to remove a page, remove the one that has been in the longest, count the number of page faults. So I want you to fill in the grid what you think is FIFO. And at the end, I want you to fill in here how many page faults there were. Because that's essentially what I will ask you to do in CA2. Okay? So, any questions before you have a go? So just this one. So just do it on paper, right? Because I'm not giving you this Excel file, right? So just literally write down 473 blah, blah, blah. And then underneath it, just draw a silly little grid with 20 by 3. All right? Or you can do it on Excel, your own Excel, right? Okay, so I'll give you until 9:40 to try that. and then I'll come back and we'll work through it together and make sure everybody gets on the same page. All right? So 8 minutes, 9:40, we'll come back and do it. I'll leave it visible on the screen there so you can see it, okay? Get rid of the other two. Okay? So 8 minutes. Okay, let's have a go at this. So, FIFA. So I think we can all agree 4, 4, 4. First 3 are easy. Okay, 0. Which one will I get rid of? Anybody there? 4. Yeah. Next one. Looks like it's you and me. Luke. Oh, there's Gavin. Good man. 7. Yeah, looks like a pretty good bet to me because 7's been in there the longest. 7. I'm going to get rid of 3. 3. What will I get rid of? Yeah, 0. Yeah, 3. 2 doesn't play on teams. But anyway, 8. I think I'll get rid of 1. Is that right? We got that right? I think I have. 5. I'll get rid of 7. 3 and 8. 4. What will I get rid of? 3. Yeah, very good. As I say, these are easy. There's a few things to watch out for. 5. What will I get rid of? Look again. Exactly, Ivan. Well done. 485. It's still there. Okay. So when we get to this case, right, and nothing is to be rid of, there's 2 different things that can happen, right? Some people leave a blank column. What I like to do is put the same thing down again and just put a little X there for me to remember that that was the same. And I'll explain to you why in a few minutes. So 3, we'll keep going. 3, I think we'll get rid of 8. You tell me if I get any of these wrong. 4. None. Well done. So 4, 3, 5. I'll put an X there. 7. Which one? 5. Yeah, I think that's right. 4, 3. 3. None. Well done. People are finally awake. 8. I think 8 will get rid of 4. 0, I think we'll get rid of 3. 1 gets rid of 7, doesn't it? 3. What will 3 get rid of? Yeah, I think you're right. And then 0, it stays the same. Okay, so, and then this little box here, all right? So in a CA, getting that right is worth 3/4 of the marks for the question. And getting what's in this little box here is worth about 25% of the question, right? So in this case, essentially, how many page faults did you get? What's the answer? "17, Zachariah got. Anybody else? 13, Luke got. Anybody else? 4. Okay, so we'll do it in reverse. 4 is the only time you didn't get a page fault, right? In other words, you get a page fault every time you have to bring something in. So You had to bring 4 in, had to bring 7 in, had to bring 3 in, blah, blah, blah. So it's actually 6. If you count them all up, it's 16, right? And in the grid, I have 20. So that's why when I marked 4, if I take 4 from 20, I get 16. All right? So you can do it many different ways. As I say, some people do it this way, and they end up with something that looks like this, right? And then they literally go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? There's loads of ways you can do it. But that is worth marks. So make sure you get it right. And don't add up the other ones. They're the only times you didn't get a page fault. All right? So that's FIFO, which is reasonably straightforward. Okay? The only thing that can probably trip you up is bringing one in when it's already there, right? And I've seen people, do things like, remember when we brought this 5 in and people went, and I've seen people do this, and 4, 8, and they go, oh yeah, it goes in instead of 8, right? And they write this down. So 5 is in twice, which makes no sense, all right? So be careful of that. That's the one thing that will trip you up with FIFO, okay? So we'll do one more. We'll do OPT, right? So the exact same question, except this time it's OPT, right? Which, as we know, is a little bit trickier. Remember, we'll do the first 3 for you, because I'm so generous. Okay, here's the first 3. So OPT, remember, you go look to the right up here, yeah? And then if you have a choice, you revert to FIFO. Okay, so I'll do the first one here for you. So 0 comes in. We've got 4, 7, and 3. Well, there's 7, there's 3, and there's 4. So 4 is the furthest in the future. So it goes 0, 7, 3. Okay, so I'll give you 5 minutes. I'll give you 7 minutes to do that, right? So at 9:55, I'll come back and we'll do this example. All right, and this, these are OPT is the trickiest one. So, okay, so 9:55, I shall return. I'll leave it up on the screen for you. Okay. So before we actually do it, what did people get for the number of page faults? Anybody? No. 14, Gavin says, so we've 14 is a possibility. Anybody else? I can't remember, being honest with you. So we'll have a look. So, OPT, we bring in 1, we have 0, 7, 3, 13, someone else says. Okay. So, what are we going to get rid of here? 0, 7, or 3, we need to bring in 1. Any ideas? It's pretty obvious to me, but I'm used to these. Anybody? 0, 7, or 3. Andre says 0. Okay, so let's have a look. 7, 3. Well, there's 7, there's 3, and 0's over here. So yeah, I think 0 is a good bet there. So 1, 7, and 3. Okay, we want to bring in 7. We've got 1, 7, 3. What do we do? Hopefully, you all went, oh, it's already in there. Okay, and similarly for that one. So immediately, given the same example, we've just saved 2 page faults there, right? 8, 1, 7, or 3. Which one? Anybody? 3, somebody says. Okay. All obsessed with 3. Well, I have a feeling it ain't 3, but anyway. Anybody else? So 1, 7, and 3. I think Conrad's right. There's 3. There's 7. And 1 is all the way over here. Right? Now, I know why you picked 3. You saw that 3 there. But we need it earlier. Right? So it's not just blindly the last time it appears. Think about it logically. I don't want to throw it out if I need it in the near future. So it's the furthest one to the right, the first appearance of it. Okay, so 3, 7, 1. So I know why you picked 3, but you weren't thinking about it logically. Okay? Okay. Oh, you missed the 2 3s in the middle. Oh dear. Okay, 3 and 7. So 8 instead of 1. So that's 8. I'm sorry, that's 8, 7, and 3. 5. Which one? 8, 7, and 3. Any ideas? 8, 7, and 3. 8, somebody says. Right, well, let's have a look. There's 3, there's 7, and there's 8. So yeah, it looks like it's 8 to me. So 5, 7, 3, 4. Seven. So we're going to bring in 4. Well, we not get rid of 5. We'll not get rid of 3. So it's 7. Yeah, so 4. 5, 3. The other thing I see people do is change the order. Don't do that, right? Because if you do, like someone could put in 4, 5, 3. Yeah, so technically the contents of the diagram is correct, but because you changed the order, you're going to muck up if you make a FIFO decision. So be careful of that. Don't, if it's there, keep it there. All right. So 5, 4, 3. Well, 5 is already there. So hopefully you're all awake. And same for that. Same for that. Okay. So we have, now we've saved 5. Now we've 5 less page faults. 7. Right, things are just going to start getting a little bit interesting now. So 7 has to come in. 5, 4, 3. What goes? Uh, 5 seems to be the general consensus. So where did we get 5 from? Well, 3 we need, so it ain't 3, so we have a choice between 5 and 4, and then as I said, you revert to FIFO, so 5 is there and 4 is there, so 5 has been in longest, so we get rid of that. So say these are the easiest marks you'd ever get. 7, 4, 3, X, 8, 7, 4, and 3. Which one? 4, somebody says. Okay, well it ain't 3, because there's 3, so we have a choice between 7 and 4 is definitely in longest. See it there? So that would be 8 there, 7, and 3. Okay? 0. Which one? 7, 8, and 3. So I think it's not 3, so we have a choice between 7 and 8, so 7 is in the longest, so it looks like to me it's that. 1. Which one? 1 has to come in, something has to go. 8, Zachariah says. Anybody else? Zachariah, right? Okay, so we've got 0, 8, and 3. Well, there's 3 and 0, so we ain't getting rid of them, so the only choice is 8. So it looks pretty good to me. So 1 and 0 and 3, and then we can go 0, 1, 3, and 0, 1, 3. So we have an X there, an X there. We have that. Okay, so we had 1, 2, 3, 4, 5, 6, 7, 8. So I make it 12. Okay? So that is the exact same data which gave us 12 page faults, FIFO 16. So we saved, we did it with 3/4 of the page faults, right? We saved 4 page faults between OPT and FIFO. All right? So we'll leave LRU and all these other ones to the lab, all right? Any questions on that? LRU is you can make your own LRU ones up, or you can look them up on the internet. You'll find there's loads of examples there as well if you want to play, or if you want to watch this video and literally take the same data, or you've already written it down now on a piece of paper and LRU it and see what you get, and then we'll see what it is in the lab next week. Okay. So as I say, I'm not going to kill you today. I wanted to introduce this. We're in pretty good shape as regards timing in terms of lectures left and things like that, so there's no need to kill ourselves every Wednesday. So any other questions, or will I'll leave you at that. I'm still marking your CA1, as they unfortunately it's taken longer than expected, plus I had to do more work on the exams than I thought I'd do. If we use an alias command instead of make dear, what the hell? I don't know, dear, we'll leave a comment in the code to explain what the alias would do. An alias command instead of the make dear. An alias command. What do you mean? Apologies. Do you mean you've got an alias that is, you've aliased make there, or you're using an alias instead of make there? I don't quite. Do you want to come on the mic there for a minute, Luke, and explain what you're asking there? Sorry. Luke, you there? Create your own command. I'm not quite following. We'll have a chat about it in the lab the next day if you want, but the whole point of make there is guaranteed to be atomic, whereas other commands aren't guaranteed to be atomic. So whatever you're using to make the decision where someone's been successful in doing something, and the make there is the one that's famous for it. Okay, there's probably other ones, but the problem is I don't know if the other ones are atomic. Okay, so that's why make there is used, because the whole point, if two of them try to make there at the exact same time, it's guaranteed to be atomic, and one of them will get in and one of them won't. All right, whereas if you use something like an alias, so I'm not sure why you do that. If you mean you aliased M to be make there, yeah, that would work. But if you if you used an alias command, whether an alias was successful or not, I don't think that would work because an alias is doing quite a few things. An alias command, and it's not atomic. Right? Hopefully that answered the question, but we can have a chat about it in the lab next week if you want. All right. Any other questions? What is the type for the second exercise? The one we just did was, if you look down it said OPT. Okay, so I see here down the bottom here, this FIFO tab, there's OPT and ZRU. So the first time we did it, it was FIFO. Then the second time we did it was OPT. So OPT is the ideal one, right? You're always going to get the best results from OPT, but unfortunately, it's not practical because you can't see into the future. Any other questions? Okay, not seeing any at the moment. All right, all right. So I'll let you go. And next week, Monday and Tuesday, we will do these in the lab. And I'll emphasize it again. It's really, really important that you learn how to do these properly. Some people get them no problem. But for the people who might struggle with the semaphore stuff and the script stuff, it's really important that you get this because these are your easy marks for CA2. All right, so I can't say it any simpler than that. These aren't the most difficult questions. They're put there so that people who find the other stuff difficult will at least score here. All right, so don't muck these up. Okay, I shall let you go. I shall kill the recording. I'll make this recording available anyway. All right.